Hey guys, in this course on ray optics and optical instruments, we are going to start a new lesson on refraction at flat surfaces, as opposed to curved or spherical surfaces, about which we'll come to in the near future. We'll study about that very deeply, indeed. This chapter will just review some of the rules and concepts that you have already come across in the past, in the previous standards. This course has been designed and taught by me, Samip Velani, and if you like my work, would like to rate it appropriately and express your pleasure or displeasure, please follow me on this link on the Unacademy platform, doing which you'll be able to connect with me on a personal level, as well as you'll be notified about my future lessons and courses when they come live on the Unacademy platform. Please make the most use of this. Please express your pleasure. I want to know what you think about my lessons. Let's start with the guiding question. You do not have to read through it. I'll read through it for you. Raghu was on a family tour to the Andaman Islands in the Bay of Bengal with his parents. His father had arranged a short scuba diving session in an inland lake about 100 kilometers in the interior of the island they were staying on. Their hotel was on the shore of the island. They had to go inland towards the lake. Raghu was very excited, but what he couldn't have anticipated was that he was about to have one of the most bizarre experiences of his life. While the scuba diving session was live, he drifted away from the others out of curiosity. He was a child. You wouldn't expect anything else from them. He drifted away from the others, swam away, and he observed that there was a fish near the shores of the lake which had, at that very moment, shot a jet of water onto a dragonfly sitting on a nearby leaf over the water surface. The water jet caught its prey, which was instantaneously stunned, and it fell right into the open fish's jaws. Whoa! How did it do that? For your information, the fish is called banded archerfish or Toxotus jaculatrus. This fish is mainly found in the Asia-Pacific region in oceans and seas, and it is quite acclaimed for this particular event that Raghu just experienced, that shooting a jet of water using just its mouth and eyes into the air outside and aiming it right at the prey while it is in the air. And this is a difficult task for you, mind you. It is very difficult to judge an object's position if you are in one medium and you're gazing into another medium. There are some consequences which the fish really accounts for, and that is the amazing thing that it does. How does it do it is your job to find out. Let's review some of the laws of refraction. We know that the incident, the refracted ray, and the normal at the medium interface all lie in the same plane. Here the light ray is traveling from one medium to another medium. The second law of refraction, which is much more important than the first law, proposed and derived by Willebrord Snell, goes as follows: that the ratio of the sine of incidence angle to the sine of refraction angle is equal to a particular constant, which is called the refractive index of the second medium with respect to the first medium. The second medium being that into which the light is propagating into. Like the first medium is the one in which the light is already propagating through. The second medium in which the light is going to propagate into. The second medium here would be just this slab, and the first medium would be this air medium here. So the sine of the angle of incidence to the sine of the angle of refraction is equal to n2 with respect to 1, where n is the refractive index of the second medium with respect to the first medium, when the light ray is getting transmitted into the second medium. if the ray of light is incidenting on the slab along the normal, parallel to the normal, it is transmitted into the slab undeflected, undeviated, unrefracted. It travels in a very straight line path, and some of it will get reflected back into the air, and most of it goes into the slab. And as a result, after the slab is done, it again propagates back into the air medium, as well as some of the transmitted rays inside the slab is also reflected back into the opposite direction. So what comes out on the other side into the air medium is a very small portion of what entered. The refractive index of a medium is a measure of the amount of bending of the ray when a ray is traveling from one medium to another in an oblique fashion. In other words, it is a measure of the lateral displacement from the ray's optical path. So the refractive index of this medium with respect to air here will tell you how displaced will be the emergent ray in the air on the other side. How much bend was induced in this ray here. That is what is determined by the refractive index. The lateral displacement is as a result of the deviation of the emergent ray here and the incident ray. The incident ray should have been traveling in this direction, but because of refraction, it is deviated into this fashion, being the emergent ray, and that emergent ray is slightly displaced from the incident ray direction. And you also get reflected part, incident part, refracted part, and so on. Let's learn more about the refractive index here. If the refractive index of 2 with respect to 1 is greater than 1, and the angle of incidence is greater than the refraction angle, then the medium 2 is said to be optically denser than medium 1, and vice versa. If the refractive index of 2 with respect to 1 is less than 1, and as a result, the incidence angle is less than the refraction angle, then the medium 2 is said to be optically rarer than medium 1. Now the refractive index of 2 with respect to 1 is a property of both the media and not just one of them. And it is independent of the incidence angle. Now although you see incidence angle in the expression in Snell's law, the refractive index cares no more about the incidence angle. In fact, the angle of refraction is a consequence of the refractive index. So when a ray of light is traveling from air to the slab, let's say a glass slab, it is refracted towards the normal because a glass slab is optically denser than air. And when it comes back out into the air, it is refracted away from the normal, and it is laterally displaced from the initial direction of the incident ray. When a ray is traveling from the glass slab back into the air, we see that the refracted ray here is refracting away from the normal, which is as a result of a negative refractive index of air with respect to glass. Not negative, just less than 1, but greater than 0 still. What is optical density here? What is optically denser or rarer that we talked about in the last slide? N21, the refractive index of second medium with respect to first medium, is a measure of the optical density of the medium with respect to the other medium, where optical density is the ratio of the speed of light in the first medium to that in the second medium. So the Snell's law can also be described and defined in this fashion, where the sin I sin R is equal to the refractive index, but is also equal to C by V, where C is the speed of light in the first medium to the speed of light V in the second medium. Usually optical density is proportional to mass density, which is just the mass per unit volume. of the medium under consideration, but that may not always be the case. I want you to find out why is that. Now here we have an example wherein water is more denser, is more mass, it has a more mass density than kerosene, but kerosene has a larger optical density than water. So as a result of this, when light travels from water to kerosene, it gets refracted towards the normal, and it behaves exactly as if this water was air in the previous example. Now here what you see, why I have put a puzzled cartoon here, is that to get this condition is very difficult because as I already told you, kerosene has a very small mass density. So it should float on water and not get submerged into water. This can be achieved if you pour water over the kerosene layer very slowly, but otherwise this is not really possible. It is achievable, but not always. You have to be very careful in this. I want you to find out why the optical density, on what properties does optical density depend on? What properties of the medium? Now let's apply our concepts that we learned here. In order to treat the kidney stones in a person suffering from kidney stones, what people usually do nowadays is they bombard ultrasound waves onto the kidneys so that the vibration frequency, the resonant frequency of the kidney stones is exactly equal to the ultrasound frequency. And as a result of that, the kidney stones will break apart into smaller pieces, which will then go into the bloodstream and be taken out of the body. To send these ultrasound waves directly to the kidney stones, you have to take into account the refractive index of every layer of body that you are going to pass through, such that the ultrasound does not damage the other organs of the body. So it is very important to understand Snell's law when you are doing ultrasound experiments, or if you're going to do an ultrasound operation on a patient in the future. There's also another example. Here this submarine wants to communicate with this ship which is on the surface of the water. Which is the path that it should send its ultrasonic waves in? Now the communication between a submarine and a ship is always with ultrasound, with sonar, as they call it. In what direction should it send its sound signals so that these sound signals are absorbed and detected most efficiently, most quickly by the antenna here on the ship? Should it be the red path, the blue path, or the green path? I want you to give me an answer in the comment section and also tell me why. Reason out. Thank you for listening. Kindly brainstorm about what you have learned in this lesson for a few minutes. If you have any questions, please ask them in the comment section. Thank you.